Okay, welcome everyone to my continuation of what is algebraic graph theory. Today I would like to wrap up the story about the spectrum, and we'll do something different next time. So the spectrum, as we have seen, is kind of very useful to study certain types of properties, and the Laplacian, which was not quite the adjacency matrix itself, mostly was interesting in the sense that there weren't really precise statements, but more like heuristics, which is still pretty cool. And here's one of my favorite heuristics ever, namely the Laplacian can decide for you how to draw graphs in some nice way. And we'll see that. Decide and how to draw, we'll see what that means. But as before, it's a bit of a not quite type of theorem statement, but more like an heuristic. We'll see. I will be more precise later on. But kind of the whole problem is, of course, that we have our graphs, and the graph actually is an abstract object. It's just defined as a set with some edges for the incidence or whatever. You can define it as a matrix or whatever you want, but certainly it lives nowhere. But the whole point of graph theory is, right, the graph theory is so great because we can draw those graphs, and it kind of makes sense for our brain. Now, our brains kind of like drawings, at least my brain does. So we really want to do that. So we really want to draw graphs, although abstractly speaking, we shouldn't, or kind of, it's an abstract object. So we somehow shouldn't draw a graph. And indeed, we run immediately into the problem you see here. One graph can have like hundreds of drawings, many drawings, right? So here already a very simple one. If I just have a graph with one edge, then I can also just draw it like whatever, like it doesn't matter. The graph stays the same, but the drawing is, of course, the bottom one is pretty shitty. Not that I claim that my drawing of the top one is better, but the drawing itself is certainly better than the bottom one, kind of in some, whatever, you get the point. The bottom one is really shitty. Anyway, so you have many drawings, so you somehow want to have a good drawing, because that's the whole point of graph theory, right? The whole point of graph theory in some sense is, well, you could also say the whole point is that it kind of models everything in life. Fine. But here, for me today, the whole point is that it lives from illustrations. Or maybe what makes it so attractive is that it lives from illustrations. So you should really think carefully how to draw graphs. And that's not a completely trivial problem if you think about it. Because, well, as you can see here, well, somehow you need to decide what is the best drawing anyway. Clearly, the one I marked here is somehow better than the others for some certain reasons. But then if you have an abstract graph, you also need to find such a drawing. And we won't address the first question. I will define for you what a good drawing is. So I do that for you. We're not discussing that, but we will kind of then discuss how to find such a good drawing. Okay, so we're really not going into this. What is a good drawing? I will define for you what is a good drawing. Anyway, so here's another drawing of a graph. I just want to make that clear that drawing is not necessarily restricted to R2, to the plane. A drawing can also happen very easily and nicely in R3. So here, the soccer ball type object graph is a drawing of a graph. And a graph drawing is really then now just a map, in my sense here, from the vertices of my graph to some r to the m. And let's say r to the m is rather small compared to n, otherwise it's a bit boring. And that's just a graph drawing, it's just a map. Okay. And we kind of want to maximize, minimize, optimize that map. So it's really just saying I put my points somewhere in space and the edges come along somehow for free, because I just really put the edges straight between such a drawing. And what you really should imagine is really the thing upstairs here is really good, like a physical model. We build it in some r to the n. Let's say we can do that. Let's say m is 3, then we can actually really do that in real life if you want. And we put the vertices somewhere and we put some little springs between them, like in this model here. And a good drawing should be one where the springs are less extended, if you want, right? So kind of a compact drawing. Okay, and it can happen in any dimension. Very boring are drawings in dimension 1. Very exciting are drawings in dimension 2 and 3. And hard to imagine are higher dimensional drawings, but in principle, we can have drawings in any possible dimension. And the idea is to get a good drawing where the springs are not very extended. I already have this physical model in mind. If that's just what physics always does, kind of by nature, not physics, somehow nature always does, it wants to minimize something. And we want to minimize the energy. So if you think of like this little chain here, so why is it hanging the way it's hanging? Well, it minimizes somehow the energy here that comes from the gravity is pulling it downwards, but it somehow can't move because its two ends are stuck. And what you get is kind of this curve in its minimized form, if you want. And we'll do the same for the graph. And we just say E. E is now very bad notation because it's not the edges anymore, it's the energy. Clash of notation, I'm very sorry. So this E here is not this E, okay? So I have edges E and I have energy E. And apparently they ended up being the same symbol, which is horrible. You shouldn't do that, but now it's too late. Anyway, so the energy is really just defined as the differences between the points, and then the Euclidean. So what is just saying here is I have a point somewhere, it's point A, and it's not quite the point because the point is abstract, the vertex. So it's the image under the map, and somewhere else is the image under the map, under our drawing map. And I want to minimize, and whatever is written here is just the Euclidean distance between them, and I want to minimize that over all edges, right? So the springs are less extended. Minimize the energy. That's a really classical slogan of nature itself. And it works here as well, which is kind of really cool. You need to add some silly conditions, otherwise you get some silly solutions. But let's ignore that. The point here is that we have this energy, which is really just the distance between the points, and we want to minimize that because that's exactly what nature tells us to do. Right? The kind of the optimal state should be the one where the energy is minimized. Yeah, and you can actually do that, and it works as follows. So it turns out that the drawing matrix, which is really just the corresponding points of vectors evaluated at all the vertices. And the energy is given by a trace of, well, a very easy product. So R transpose, R is easy to compute, R transpose is easy to compute. L is our Laplacian, and R. So you can just need to compute the trace of this product, which is really simple. And that's a really cool answer what the energy is. So minimizing the energy is then minimizing this trace, which you then can do. And it really just involves the Laplacian, which is just really, really, really cool. And this works extremely well in practice. And turns out because it's a trace. So how could you minimize the trace? Well, it's related to the eigenvalues and the eigenvectors of the Laplacian. And we do an example on the next slide. But kind of the point here is you can use the Laplacian and just some eigenvectors of the Laplacian to do that. So we really just have the Laplace eigenvectors ui, and we can just minimize. We'll see that in an example in a second. The corresponding, so here the corresponding eigenvalues and the eigenvectors, again, the smallest ones. For the Laplacians are always the smallest ones are important. And you can just really solve it and just compute what the minimal energy is in terms of the Laplacian. It's really, really fantastic, right? Minimizing energy kind of makes sense. It's kind of what nature tells us. And how to do it in practice might be difficult, but here's a really cute answer, like compute a trace of a certain matrix. The matrix is essentially the Laplacian. And how do we do that? We compute its eigenvalues and eigenvectors up to a certain point. So really a nice story somehow. So let's say we want to draw a graph, this slightly silly graph here. And well, it's really just a square. And so you can compute the Laplacian, and you can compute the Laplacian eigenvectors, which in this case, the smallest one and the second smallest one are just, so the ones for the smallest eigenvalue and the second smallest eigenvalue are the ones you see, right? So what you do now is you just put them in a matrix. You kind of can ignore that this is really just a scaling. So 0.707, that's exactly this point here. So you just put them in a matrix by just, well, putting them in a matrix. It's really, really simple. Put them in a matrix, and now you can just read off the corresponding coordinates. So this is a matrix, so it's -1. Let me just put it in a nicer matrix. So I just wanted to put it in one. What is it in the not in display, but in the line, so it looks a little bit strange. But this is actually the matrix up to a factor of 1/2, and you can now read off where the 4 points should go. They should go to -1, 0, scaled by 0.707, right? All of these are scaled by 0.07. It should go to 0, -1. This is this one here. It should go to 0, 1. That's certainly this one here, and the last one should go to the 1, 0. Okay, let me repeat what we did. We have a graph, and it's not terribly difficult, but it's just a good example. We compute the Laplace eigenvalues of that graph, the smallest ones, put them in a matrix, and put them column-wise in the matrix, and we can read off row-wise the coordinates to have a nice drawing. And I think that's pretty amazing. It's pretty exciting. It's really simple, and you could do that by hand if you want. You should let the computer do that for a bigger example, but anyway. So this was my story about the Laplacian. And the Laplacian does a really good job. So this is one of my favorite ones. It's really simple. You take the Laplace eigenvalues, the eigenvectors, the smallest ones, put them in a column matrix, and then the rows you can read off where to put the points, such that you get a really minimized energy graph drawing, which I find is just really, really cool. Anyway, I hope you enjoyed this video, and I also hope to see you next time.